Hi, everyone. I'm Craig. Really fun to be here. It's already been a fun day, so hopefully we have a good few days to come up. I'm from New Zealand. Thankfully, that means my accent just works here. I don't have to say American words. I'm an Angular GDE, Google Developer Expert, do a bunch of Angular stuff. And I'm also an architect at Hero Devs. So Hero Devs, we kind of specialize in handling end of life for open source software. We do never-ending support for libraries like AngularJS, Vue 2, Bootstrap, Drupal 6 or 7 or whatever one it is, and a whole bunch more. And in my role, I get to work with clients all over the world to help plan and roll out large-scale migrations and manage the transition to new modern technology stacks. And at the moment, I'm working with the engineering team at Rust-eze. I work out of the Rust-eze Lightning McQueen Training Center and Technology Hub in Radiator, Arizona. And we're responsible for making sure that Lightning McQueen is performing his absolute best so he can keep up his winning form. If you want to follow along with slides, maybe this will work. That one, if you can scan that, get it up on your phone, it might be a bit easier to read some code and stuff. So I'll give you a couple seconds to hit that if you want. Nice, but before we get started, I have a quick message to play from our sponsors, Rust-eze, featuring Mr. Lightning McQueen himself.
Lightning McQueen here, and I use Rust-eze medicated bumper ointment, new rear end formula. Nothing sues a rusty bumper like Rust-eze. Wow, look at that shine. Use Rust-eze, and you too can look like me. Ka-chow!
Ka-chow indeed. Lightning McQueen. A bit of a legend, 7-time Pistol Cup winner, catchphrase master, and all-around great guy. Whatever Mr. McQueen wants, Mr. McQueen gets. And usually what Mr. McQueen wants is to go faster. Lightning's a highly tuned machine. Every system is engineered for peak performance, and we're always on the hunt to fulfill his need for more speed. Chief engineer at Rust-eze, Sir Tomater, has been Lightning's best friend for as long as anyone can remember, and he's often the source of the best ideas and suggestions for how to make things go faster. Speak of the devil, here he comes now.
Hey there, Craig. I have an idea to help Lightning McQueen go and then faster.
It's so funny, I can't hold my shit together. This is AI-generated voices, it's great. Oh, that's amazing, Mater. What's the idea?
I think it's time to get the aerodynamic simulation working on Lightning's heads-up display.
Wow, that's a great idea, Mater. Lightning has always wanted to be able to update his aerodynamics on the fly during a race. One little known fact about Lightning McQueen is that all of his onboard software is written using TypeScript and running on an internal browser. As part of ongoing research and development, Lightning uses complex aerodynamic simulations to figure out the fastest shape to be on while he's racing. These fluid dynamic simulations use lattice-Boltzmann methods to simulate the flow of air over the body of a car. This is an example of the kind of visualizations that the simulation produces. The lattice-Boltzmann method is a two-step algorithm which models how a fluid moves through space and interacts with barriers in that space. The first step of the simulation is a collision step, which models the collisions between molecules in a fluid. Don't have to worry about the math for this, just know that you kind of got from one position in space, some interaction happening, and a change in that position. And the second step is the streaming step, which models the change in fluid density. The specifics of how this is implemented also don't really matter, but it does take a little bit of maths to make it work. So at a very high level, you can think of it as a simulation across a two-dimensional grid that requires computation to then move on to the next time-based step.
We just need to figure out how to get the simulation running fast enough to be useful during a race.
That's right, Mater. Whenever we've tried to run it in a browser in the past, it just hasn't been fast enough. Crunching all those numbers takes some time. Let's investigate a little bit. There's two main parts to our visualization, the simulation and the renderer. The simulation class is the implementation of the lattice-Boltzmann algorithm, which takes X and Y dimensions of the grid, as well as some values representing fluid velocity, viscosity, and simulation speed. The canvas renderer is a HTML canvas-based renderer, which basically just colors in the grid based on the fluid velocity at each point in the simulation grid. Everything executes in a loop. One step of the simulation, too small? Too small? Can we read? Yeah, okay, good. Everything executes in a loop, so once the simulation is evaluated, then the result gets drawn onto the canvas. So the code for that, obviously, that you can't read, but if you scan that, it should open up a real running version of the simulation. See if I can actually get it as well. It's going to work. Cool. I'm not going to be able to see both of these. Okay, so this is, let's see if we can zoom the hell out of that. Cool, so this is just a little Angular implementation of the simulation. Nothing too fancy here, but don't worry if you haven't seen any Angular before. Basically, we're reaching into the DOM, grabbing a canvas, finding out how big the canvas is, and then creating the simulation. Simulation's kind of the interesting bit. And then we initialize this little black line as some kind of starting thing to collide the fluids against. And then we have this canvas renderer, which is the thing that makes it draw the shape on here. We have some dumb render loop with requesting an animation frame as often as it can, ideally 60 frames a second. And in that frame, we run some simulation and we render the result of that. You can see here also I've got some timing code. And if we go like this, hopefully, yeah, we'll see that we're getting kind of 30 to 40 milliseconds a frame for the simulation code, which is basically too slow, as we're going to see in a little second. If I close that again, we can look in here at the simulation. And it's a whole bunch of code. There's nothing too special about it. It's basically a whole bunch of array manipulation, a bit of maths to move some things around, but it looks kind of like any programming language. In this case, it just happens to be TypeScript. There's also some color code, which doesn't really matter, but we'll talk about that in a little bit later. And the canvas, which is basically just a thing that loops over the data in the simulation, picks out the appropriate color for the speed of the liquid at that point, and then draws that to the canvas. The nice thing about the canvas renderer is that's fast. It takes about 2 milliseconds to render a frame, which gives us something like 14, 15 milliseconds per frame to run the simulation. But like I said, we're not getting anywhere close to that in this current version. Yeah, so as you can kind of see here, we've got some logging, and we can see that our simulate method is taking about 32 milliseconds a frame. If we want 60 frames a second, that gives us 16 milliseconds a frame. So we need to be about twice as fast. But the good news here is that our render code is, like I said, already pretty quick. So renderer code is good. Canvas APIs are fast enough for the browser, but our simulation code is way too heavy to get it running at 60 frames a second.
I don't know if it's fast enough for me to use it in real time. I need it faster.
You hear the boss. It's got to be faster.
Got to be faster. All right, let's get into it.
You get to work on that. I need to go put on some Rust-eze. Ka-chow!
Ka-chow. There's one thing I know about Lightning McQueen, is that he sure loves Rust-eze. Wait a minute. That's it. Rust. Mater, what if we try running the simulation in Rust?
Woo! That's a great idea.
Thanks. I think so too.
You'll have to teach me a bit of Rust so I can help.
Of course. Let's do a quick comparison between TypeScript and Rust to get our bearings. So, TypeScript, in case you don't know, is a superset of JavaScript focusing on static typing and web development. Rust, on the other hand, is a systems programming language emphasizing memory safety, performance, and concurrency. TypeScript relies on JavaScript's runtime, which means it has garbage collection, while Rust provides memory safety without needing to use a garbage collector, using a borrow checker. TypeScript supports asynchronous programming, but basically lacks native parallelism, while Rust has built-in support for concurrency and running things in parallel. TypeScript kind of inherits all the performance characteristics of whatever JavaScript runtime it's in. So it's an interpreted language. That means it's generally running a bit slower, whereas Rust can be highly optimized. You have pretty fine-grained control over memory access, so you can make it run pretty fast. In terms of the kind of ecosystem, the tools that we use in both of these different worlds, in TypeScript land, we might use something like NVM to manage the different versions of Node that we're using or different libraries. In Rust, the equivalent is rustup. For TypeScript, or more generally Node, we'd use something like npm or yarn to install dependencies. In Rust, we use cargo to install what are called crates, just their way of calling a dependency. In TypeScript land, Node land, to compile and build our code, we might use one of many tools. We might use the TypeScript compiler directly. We might use Vite or Webpack or Babel or anything like that. But in Rust land, again, we're just going to use cargo. So cargo build is how you build things. In TypeScript front-end land, we have a whole bunch of different options for how we test our code. We might use Jest or VTest. We might write some end-to-end tests using Playwright. But in Rust land, we're going to use cargo test. The whole Rust ecosystem is basically based around cargo. And in general, there's a much tighter coupling between the language and the tooling and the community and how they use it.
Well, that's all pretty neat, but what does it look like?
Yeah, it's a good point. Let's actually look at some code. So hopefully you're reasonably familiar at what things look like in TypeScript. That's going to be my frame of reference here. But if you've seen any programming language, most of these things should look quite similar. In TypeScript, we can kind of create variables. We can create constant variables. We can create variables using let. And there are some kind of confusing implications on how that value is assigned and the mutability of that variable, specifically if there's objects assigned and how properties are dealt with. In Rust, we have a rough equivalent like this. So by default, if we use let in Rust, that thing is going to be immutable. And if we want to mutate it, we have to declare it using the mute keyword to opt in to that mutability. Yeah, so by default, we're immutable, or we can add this little keyword here. Both languages have module systems, so in TypeScript, we can import code just from another file. We can use a relative path to just pull in this thing from the simulation, or we could use a package name to import something from a Node module, say. In Rust, it's a little bit different. So there's not necessarily a one-to-one mapping from files to modules. We can import a full module and move specific module members into scope, which means they can be used, with the use keyword. And in a Rust program, you kind of have to have this main method. In TypeScript, files just get interpreted from top to bottom. So in this top one, the simulation would just be created. But in Rust, we have to have this main entry point. In our TypeScript example, we use the new keyword to create a new instance of a class, whereas there's not really an equivalent in the language of Rust, but there is this kind of convention of a method kind of thing on an object called new. But yeah, this is just a convention. It's not actually a keyword part of the language. Of course, these are programming languages. We have to do control flow. We have to decide when things are going to happen. TypeScript, of course, has the usual things like if statements, while loops, and specifically like when you're calling functions, if you're passing a value or an object to a function in TypeScript, you're passing a reference to that object. Rough has something roughly equivalent. These look pretty much the same. But of course, there are a few syntactic differences. Rust has optional parentheses, so you don't need to have them all the time. You can add them if you like. But these things mostly work how you expect. The difference here is that when you call a function in Rust, you need to explicitly state that you're passing a reference. And we're going to come back and touch on more of this soon. This is where the memory management comes into play. So with just a regular old function, there's a whole bunch of similarities between Rust and TypeScript. In fact, they look almost identical. The difference here is that Rust uses just fn as a kind of shorthand to declare a function. and some differences in the naming conventions. So Rust uses this like snake case for naming functions and variables. There's a few little differences in the types of objects that can be passed around. So when you have a parameter in a function that must be a reference or must be mutable, like in this case, you have the ampersand and the mutable keyword, which declares how the objects are going to be passed to this function. One other little difference is that there are much more specific types in Rust. So in TypeScript, we basically have number. In Rust, we can use integers, unsigned integers, floats, a few other ones in there. In this case, U64 is obviously an unsigned 64-bit integer, obviously, maybe not obvious. One other nice thing is that Rust has this kind of range syntax, which if anyone ever did any CoffeeScript or any Python might look familiar. I really, really like this syntax. I think we should steal it. Obviously, we're going to be doing things with stuff because it's programming. In TypeScript, we can kind of define these object shapes using a type or perhaps an interface. And the equivalent of that in Rust is a struct. And so by default, in TypeScript, everything's public. By default in Rust, everything is private. So if you want to explicitly make values on an object to be public, you have to use the pub keyword. So public, these properties on this object would be public by using the pub keyword. And again, we use more specific types. So we have unsigned 64-bit integers, again, rather than just the weird floating point fun that is the JavaScript equivalent. So in TypeScript, we can define a class, and that's going to be both a type and the implementation of that type. So you can use this colors class, you can instantiate a version of it, or you can pass around a reference to colors and use that as a declaration of the type that this object should be. But in Rust, the type and the implementation are always separate. So the type is defined as the struct, like we saw before. In this case, these are all going to be private because we haven't marked them as public. That is probably a bug. But we have the implementation of this thing, which uses the impl impl keyword. Like we sort of talked about before, we don't have like a constructor and we don't call new, but we do have this convention of a new function, and that's used for instantiation. In the case of the new function here, we want to return an object that matches the struct. So here we're saying this new function will return a struct of type color, and then at the bottom, we're defining and returning a struct called colors, which has these just RGB values on it. One other cute little thing to note here is this exclamation mark bit of syntax, which is basically a way of executing a macro. So we're kind of doing some meta programming here. This takes this kind of declared object and makes a vector out of it, kind of like an array.
Gosh, that looks like a programming language.
Exactly, Mater. There's nothing too scary here, especially like in our case where we're going to be converting something fairly mathy into Rust. So this is the kind of, some snippet of the TypeScript implementation of the simulation. Again, you can scan that and read the whole thing if you want to. It's, like I showed you before, it's basically just a whole bunch of arrays, looping over things, moving values around, the kind of stuff you might expect to see in like kind of mathy code. And this is the Rust version. So again, you can scan the code and compare them if you want, but it's a fairly straightforward translation. The main differences are just little syntactic things like using the range to loop over a list, using self instead of this, or just some extra precision around the different types of numbers. So again, TypeScript, we would have declared just number types. Here we've got unsigned 64-bit integers all over the place. And it would be kind of easy to look at these two bits of code and go, okay, what's the benefit? What's kind of special about Rust? This just looks like pretty much any language you can pick. And most of the magic here comes in the realm of memory management, as I've kind of alluded to a little bit. So Rust has some guarantees around memory safety by enforcing some pretty basic but quite strict rules for how you pass data around, and specifically how you borrow data and who owns data. So we're going to look at ownership first. A little bit of a contrived example, but let's say you just wanted to really, really make sure that the initialization had happened properly and you wanted to call it twice. If we were to run a cargo build on this code, we'd get something like this, which is a pretty loud, pretty detailed error with a whole bunch of like nice things like pointing to the place in the code where it was. The compiler errors that you get in Rust can seem pretty scary, pretty daunting, but they're actually usually very, very helpful if you read them. They're very specific. But you have to like sometimes look up the docs and read some new big words, but eventually you kind of get the hang of the things. What this error is saying in this case is that when we passed the simulation into the initialize function the first time, we gave up ownership. So we lent a book to a friend. We gave up the, in this case, simulation object. And you can't give away things twice. You only have one thing that you own. You give it away. You can't just then give it away again. And so the compiler rightfully complains and says, hey, you can't do that. And if we want to be able to give away ownership twice, first we have to make a clone of our thing. I guess take a photocopy of the book, which creates a new instance in memory. And then we can give away the clone and the original. And in this case, the borrow checker would be totally happy. So again, fairly conceptually simple, but when that pops up in your code, you kind of go, what the hell's going on here? Quite a mental shift. But sometimes you don't actually want to transfer ownership. You still want to be the owner of the thing, but you want to let someone borrow it for a little while, kind of like, again, with the book metaphor, hey, give this back to me when you're done with it. So this means that the function has to expect to take a reference to the object of a given type. And the caller can take a reference to the object using the ampersand symbol, which then gets passed as a reference. And so this is kind of similar to how passing an object works in JavaScript or TypeScript. You're always passing this thing by a reference. So you're just lending the ownership of the reference while that function is being executed. And you can take as many immutable references as you want. But with initialize, the initial barrier function, it actually expects a mutable reference. And so if you try to take two mutable references and then pass each of them to the initialize function, we've broken another rule. So yeah, we've taken this kind of second mutable reference, one copy, second copy. But then the borrow checker comes in and says, hey, you actually can't do that. Cannot borrow simulation as mutable more than once at a time. Again, really kind of descriptive error message, tells you what's going on here. Tells you where the problems are, everything's kind of nice. And the fix for this is a little bit frustrating. So all you have to do is take the first mutable reference and then use it, and then take the second mutable reference and then use it. So you're just slightly restructuring how your code was defined. You can kind of get around this error. And that makes us have a happy compiler. I found this one really weird, but then I realized I write JavaScript all the time, and that's a pretty quirky language, and so you kind of get used to that. And so like every language, these things have these quirks. And I think the benefits in Rust really do pay off. So the borrow checker is a pretty different concept. There's not really an equivalent in JavaScript land or TypeScript land, and that's just a fundamental difference in how the language works. We couldn't just shoehorn that in and expect to get rid of garbage collection. But thankfully, the type systems are reasonably straightforward to understand, reasonably equivalent to what we might have seen in other languages as well. But again, there are a few differences. So TypeScript has what's called a structural type system. So if two objects have the same shape, they can be applied to the same type. That means if they've got the same properties and values on them, regardless of what the thing is called, you can still pass those objects around and treat them as the same type. Rust, on the other hand, has what's called a nominal type system. So nominal name, basically. If two types are totally identical, but are named a different thing, they're copies of that same type, they are treated as two different separate types, and they cannot be assigned to each other. So you have to actually have the same type. I think this is similar to Java and C# and a lot of other languages. But the way TypeScript exists, kind of at that layer on top of JavaScript with a whole duck typed model, that made sense for TypeScript, and also has some powerful things that come with it. TypeScript has got, like I said before, some relatively simple number types. So we have this all-encompassing number, which until like 2 years ago was basically everything you could do. More recently, we've got a big int number type. which is actually a U64 as well. That's the way it's implemented under the hood. But Rust allows us to do a whole bunch more things. We can be very specific with the amount of memory that a type uses, and we can do signed or unsigned integers. We can do floats. We can do this usize thing, which is useful when accessing indexes in an array, a whole bunch of different things. Thankfully, Booleans are just the same. We have Boolean true and false in both languages, so those things copy over pretty easily. But then strings, again, are much more complicated. TypeScript, we have this string type. And I'm not being super generous here because TypeScript does have string. It also has like a specific string types, so string literal types. TypeScript also has string template literal types. But fundamentally, they're all just a string of characters and you can treat them all the same way. Whereas in Rust, we have this capital S string type. We have the lowercase str type, which you use quite a lot, and then a char type. Char, I don't know how to say that, but for a character, just an individual character of code. I guess the equivalent of a character in Rust would be just like a single character string literal type in TypeScript. So on the TypeScript side, we have arrays. So we have a generic array of type T, and the equivalent to that in our Rust code would be a vector of type T. And again, we kind of touched on this a little bit. We have objects and classes in TypeScript land, and the equivalent in Rust and in the type checker are structs and implementations.
Okay, so let's write the render in Rust.
Cool. Let's give that a little go. So let's quickly look at the TypeScript implementation first. So we have some canvas renderer class with a single function called paint, which takes the simulation as an argument and returns nothing because it's gonna have a side effect. We're gonna draw to the screen. It just loops over all the positions of the simulation grid. So we're going from X to Y through all the Y values and all the X values. So kind of painting across the 2D array. If we find that the cell in that position is a barrier, so one of the things that we want to bounce against, we just draw that barrier as black and leave it there. Otherwise, we assess the simulation to get the velocity at that point in the simulation, look up the appropriate color for that, and then basically color in that pixel on the screen. The way this is actually implemented is kind of using this put image data. You basically create the whole image once and then draw it to the canvas once. It's way faster than updating each individual pixel one at a time. And so what would that look like in Rust? We obviously don't have kind of canvas APIs or anything like that in Rust. So to keep it really simple, we're just going to render to the terminal. And similarly, we have our terminal renderer terminal, I guess they called it here, with this paint function. And it basically does the same thing. So the very first thing it does is a terminal control character, which just clears everything so that we can kind of update the whole thing. And instead of storing that result as the image data that we had before to draw to the canvas, we're just going to build up a string. In this case, we're using a capital S string, which is a mutable string, which means that we can append to it as we go, because the lowercase string is a immutable string. You can't update that. And kind of similar thing here, we're just going to loop over the 2 dimensions of the array, check if the cell is a barrier cell. If it's barrier, we draw a black square to the terminal. Otherwise, we do that same kind of color manipulation for the position of for the speed of the position in the array, and then we draw a colored square to the terminal. Again, weird terminal control characters. After each line, we append a whole new line character. So we're kind of doing the first line, new line, first line, keep going on. And then at the very end of that, we'd print the whole thing to the terminal. With the Rust implementation of this, we can do a cargo run, which is again using the cargo implementation, the whole cargo tooling. And if we use the release profile, we get something like this. This is, again, just rendering to the terminal, so it's pretty kind of loosely granular. We don't have as many pixels as we did, but the simulation is still doing the full simulation for the same size grid as with the JavaScript implementation. But we're kind of down at around 13 milliseconds a frame, whereas before I think we were at 30-something. So basically, it's about 3 times faster just to run that simulation code. And this is an optimized build, so you can run just cargo run. That will give you the kind of debug build. Even that was faster than the JavaScript implementation. So I think it's pretty safe to say that Rust is categorically faster, which is great.
Ka-chow! Did someone say faster?
We sure did.
You three, she's flaming hot now.
Flaming hot.
Whoa, how can we get that running that fast in my browser? Ka-chow!
Really good question, Mr. McQueen. So the Rust ecosystem has got one more magic trick for us to try out. So WebAssembly has been floating around as an idea for a few years now, and you can approach that from a whole bunch of different ways. You can directly write in WebAssembly, or you can compile to it from various different languages. But the Rust ecosystem probably provides, at least to me, the most complete and the most accessible way of creating a WASM bundle that can run in the browser. So we only have to do a few little changes to our code, and then we can prepare it to be compiled using WASM. So we have to import the WASM module using this use syntax we saw before. And then we just use this binding syntax, these kind of weird little annotations. And that's to expose the public parts of our code, bits of the code that we want to call from the web layer. I guess in some ways it's kind of like the decorator syntax in various languages. You're annotating the code with some metadata. And then I know I said that we basically use cargo for everything. In this case, we're not going to. We're going to step away from cargo, and we're going to use WASM pack, which is, I guess, some webpack / reference. But this is basically another builder that takes the Rust compiler, compiles the Rust code into an intermediate language, and then compiles it into the WASM. And it actually produces like an importable JavaScript bundle that happens to reference some WASM code. And so, it kind of looks pretty straightforward, but it's actually a little bit weird to reference this compiled Rust WASM code from the TypeScript side. So the import is kind of as usual. We can say, hey, we want to pull the simulation from our fluid package. But obviously the code that we exported follows these Rust conventions. So instead of using new, like we might expect to instantiate something, we're going to use .new, which is that reference, that kind of convention from the Rust side of things. And we have to do a few other things as well. So we have to make sure that the numbers that we're passing in aren't regular JavaScript numbers. We need to wrap them as big ints, because like I said, a big int is roughly equivalent to an unsigned 64-bit integer in the Rust layer. And so for our kind of different U64 variables, we're passing in these wrapped big int numbers. And then the other thing that we have to do to make sure things don't get too slow is one of the slowest things you can do is pass memory back and forward between the Rust and the JavaScript layers. So here we're creating this uint8 array with this thing called memory buffer, which comes from inside the WASM package. And that basically gives us a window over the entire chunk of Rust memory. So we don't have to pass things back and forward. We're just directly reaching into and investigating that memory. We can't really manipulate it. We can't really update it from this side, but we can just look at a value. And so the simulation is going to run in the Rust layer. And then for any value that we want to read out of the Rust layer for our rendering, we can just look at this mirror. And so we have here two different bits, the barrier, which is the bits of code that are going to be colored in black in the simulation, and the curl, that's from the original implementation of this algorithm. That's the bit that has the velocities of each point in the simulation. Yeah, and so we use this kind of pointer to point at that part in the code, and then directly access WASM memory. So now this is the bit where I haven't actually got my code running. Let's see if I can make this happen. Let's see if this works. Okay, if I refresh that. Cool. Okay, so So that is our WASM compiled Rust implementation running converted to WASM in the browser using the Canvas API. And it's heaps faster, which is kind of the goal output. Let's see if this is working now again. So yeah, if we do some more logging and we check out the time that the simulation takes, again, we're getting the kind of speed that we were seeing in the Rust layer, but in the browser. So instead of the 30 plus milliseconds we were aiming for, and we were trying to get everything under 16 milliseconds, we've got down to 13 in a little bit, giving us the 2 milliseconds for the rendering time. So we're well under our 60 frames a second. So that is, again, certified faster.
Ka-chow! This is amazing. I can custom tune my drag reduction system as I go.
Sure can, Lightning.
That sounds like success to me.
Me too. Let's go over the things that we did one last time. So, Lightning McQueen always wants to go faster, and the dream for him is to be able to use these aerodynamic simulations on the fly as he's racing. He can only run a web browser during the race, and TypeScript is too slow to do this kind of mathy, high-level processing. Rust is really fast, and we can run the simulation super quick, especially if we can do that in a terminal environment. But if we combine it with WASM, we can get it running super speedy in the browser and make Lightning a very, very happy race car. You can look at it again because I find it really quite mesmerizing. It's just kind of pretty. The code's there. If you try to get it running later, good luck to you. It's an absolute mess. But I don't know, ping me on the internet and we can talk about it. Ka-chow. Hopefully that is the end. Once again, I'm Craig. Thanks for having me. That was really fun. Shout out to NDC. This place is already really fun. Come find me, say hi. I'll be floating around. Otherwise, remember that life is indeed a highway. Thank you so much. And yeah, I think we have question time. Or if you want to go upstairs and catch the last bit of Scott's talk, then I'm not going to be offended.